Guys, in this video we're going to take our very first look at what we refer to as our sum and difference formulas, and we also, as a matter of fact, refer to these as our sum and difference identities. So let's go ahead and indicate that here, and just recall that an identity is just two different expressions that mean the exact same thing no matter what you plug in for the variables here. And so we're looking at situations where we're going to be able to take expressions like you see on the left-hand side of these equations and rewrite it in the right-hand side of these equations. So what we're going to do is we're just going to take a minute, kind of try to familiarize ourselves with what these look like, maybe describe some patterns, and then put them to use. So the very first thing I want you guys to do for yourselves is where it says sine of u plus or minus v. I want you to recognize that on the left here we either have a sum or we have a difference, but it's not both. We're just kind of trying to, instead of rewriting this formula twice, rewrite it compacted into one formula here. So we'll say plus or minus on the left here, and what this is going to be equal to is the sine of the first angle in this sum or difference times the cosine of the second angle in the sum or difference, and this will be also plus or minus the sine of the second angle in this sum or difference times the cosine of the first angle in the sum or difference. One thing that I want you to recognize is that in this top one here, where it says plus or minus on the left, it also says plus or minus on the right. So what that's going to mean is, we're at least going to indicate this here, whatever the sign is on the left, it's the same as the sign that you get on the right here. And that's going to be one outstanding difference between our sine sum and difference formulas and our cosine sum and difference formulas. But down here for cosine, when we look at it, we see that it has a plus or minus on the left and a minus plus on the right. And so what we're going to indicate is just this. With our sine sum and difference formulas, whatever we're doing on the left, adding or subtracting these angles, we're going to do the exact opposite on the right. Excuse me, got a little congestion. So what we're going to do is we're also going to switch the right side of this first identity, and I'll tell you why here as we're doing this. But what I want to do is I want to rewrite this as the sine of u, so we'll say sine u times the cosine of v. So that hasn't changed. It's still plus or minus, but I want to write this as cosine of u times the sine of v. And kind of our intent here by rewriting it this way is, in each of our formulas, I like to preserve the order of u and v, and that is to say whatever angles we choose to add or subtract inside this angle on the left here, we're going to keep them in the same order when we expand this on the right. So you see we have a u and a v, a u and a v. As we get down to our cosine sum and difference formula, taking a look at it, we have cosine u, cosine v, minus plus sine u, sine v. You'll notice that u and v are still in the same order here. Okay. So taking a quick glance down here at tangent, we have tangent of a u plus or u minus v. And what you see is our sine is going to be the same on top when we do this sum or difference. So we say same. I don't know if you can squeeze that in there, but it's going to be opposite on the bottom down here. So opposite. So now we've looked at some of this sine action here. Let's take a look at some of the patterns that exist here. So out of all three of these identities, I would say that these are very similar, those for sine and cosine. So what are some things we're going to look for? I think that the first thing I want to point out is that on the left here, if we have a sine of a sum or a difference, the formula on the right starts with the sine function. And if we have a cosine on the left here, is our sum or difference cosine formula here, we're going to start with the cosine on the right. So if we know that that's the case, how do these behave beyond that? What I want you to know is that sine alternates. And what I mean by sine alternates is this. We have a sine and then a cosine, but then we switch it around to make it cosine and then a sine. So in each of these terms here, we have a sine with a cosine, and in the first set here, sine always comes first because sine came first on the left. So sine, cosine, cosine, sine, sine alternates. Whereas we see that with cosine, let's go take a look at it, it starts with the cosine on the right, but this is very homogeneous. So that means that we see that if this is a cosine, this is a cosine, and then we have our sine and our sine here. So we would say that it doesn't alternate its functions, and it starts with a cosine on the right there. And then the last thing here is our tangent sum and difference formula. What we're going to want to recognize is if we have a tangent of a u plus or minus v, up on top here, not that we distribute this because that's not what we're doing here, but I kind of think about it that way. We're just going to take the tangent of the first angle and add it or subtract it to or from the tangent of v, or the second angle here. And then this is always over 1 minus plus, so opposite signs here, opposite, but the product of these very same two ratios right here. So it seems like a whole lot to remember, but if you pick up on the patterns, it makes it a little bit simpler here. So let's take a look at how we could use something like this. And I think a really good thing that maybe we could try first is if I asked us to find maybe the cosine of 30 degrees plus, oh, I don't know, 60 degrees. It should be the same thing as the cosine of 90 degrees. And I think that this is a good one to pick on just because we can write this 90 degrees as a sum of two angles here that I'm going to write as u and v. And we can kind of expand this and see that we get the same thing we do for the cosine of 90, which, if we refer to our unit circle, should be the 0 right here. So I'll go ahead and say, foreshadowing, we should get a 0 here. But how does this work with sum and difference? Well, according to our sum and difference formulas up here, the way this works for cosine is if it starts with cosine on the left, it starts with the cosine on the right. So we're going to write cosine, and I just put in blank parentheses, and cosine doesn't alternate. So that means cosine has another cosine, and because this is minus plus, whatever this is on the left, okay, this on the right has to be the exact opposite. So we have the cosine, let's try this again here, the cosine of u times the cosine of v. So this would be minus the sine of u times the sine of v. We're going to have to put a minus here, and then we'll put in our two sine ratios right here. So sine of u, sine of v. Okay, so you know what? Let me do something here really quickly just so we can write on this. I think I should be able to write on this now. So sine of v. So when we look at this, we say, well, what are u and v? Well, hey, we can just identify them over here. Our u was like our 30, our v was like our 60 right here in this sum. Okay, so we're just going to drop in a 30. We're going to drop in a 60, and just, you know, we keep the order of the angles consistent here, and then we just go through and we tend to just evaluate these things here. So we can just use our unit circle, or our knowledge of the unit circle, to evaluate for these. Our cosine at 30, looking at this, would be root 3 over 2. So we get root 3 over 2, and then cosine at 60 is 1/2. So we'll put a half here. And then what we get over here is a sine at 30. Well, if we look at our sine value at 30 here, it's a half. And if we look at our sine value at 60, it's root 3 over 2. So we're going to simplify this now, and this is something we commonly see with these formulas is two fractions minus or plus two fractions in products with one another. So multiplying straight across, we see this, we get root 3 over 4 minus root 3 over 4, which in this case leads us to a result that would say that the cosine of 30 plus 60 would be 0, which is something that we already are absolutely aware of. So why would I ever use a sum or difference formula if I was evaluating for the cosine of 90? And what I want to float past you is that often, if it's cosine of 90, we just use our unit circle, but there are some angles that do not fall conveniently on this unit circle that we'll want to find values for. And so one of those I want to take a look at is this one right here. Let's try to work this out here. How can we use our sum and difference formulas to help us evaluate for the sine of pi 12ths, which, if we keep in mind here on your unit circle, here's pi 6, pi 12 would be like half of that. This would be like 15 degrees. So one thing I want you to do is make a note here. If your inner angle is ever in radians, we're going to convert to degrees. It's just easier to do sums and differences in your head when things are written in degrees than in radians, because I will tell you that it's probably not likely occurring to you that pi 12ths is the same thing as pi thirds minus pi fourths. So how can I think about this a little bit differently? Well, pi 12ths, if we take this times 180 over pi, we can cancel out our pi's, and 12 goes into 180, I think that's 15 times. So 15, this is a 1, a 1, a 1. We multiply straight across and we get 15 degrees here. The fact is, what I'm asking us to do is to find the sine of 15 degrees. Now you might ask yourself, well, how do our sum and difference formulas come into play here? This is not a sum or a difference in here, but our goal is to actually take this inner angle of 15 degrees and rewrite it as a sum or a difference. And you can see that I did write it as a difference here. You know, I was pretty savvy. I actually knew it was pi thirds minus pi fourths, but that's the same thing as what? 60 degrees minus 45 degrees. So the real task here is going to be this. If we have 15 degrees as our inner angle, are there two angles that are really easy to evaluate for around the outside of the unit circle that we can either add together or subtract apart to get 15 degrees? And I would say, well, if I can add or subtract any of them, one really simple combination would just be, what if I took 45 minus 30 degrees here? So we're going to take a look at this here. I say the sine of 15 is the same as the sine of 45 minus 30 degrees. And here's where we can actually, I can't believe I wrote sum here, sine. Must be thinking about some probability here. So we have a u minus v type of configuration. And this is just our sine sum and difference formula. So let's go ahead and process this here. If it's a sine sum and difference formula, when we expand this, it starts with the sine on the right, and it alternates. So we have a sine cosine. Sine is very much plus or minus on the right. So if it's plus or minus on the right, it's plus or minus on the left. It means that if we're doing a difference here, we have to do a difference over here. It's the same. And then we alternate. Cosine, sine. Switch that order around. So now we can just go ahead and populate these with 45 degrees and 30 degrees. 45 degrees and 30 degrees. And what we're going to do is we're simply just going to evaluate these four ratios right here using our unit circle. Now, I would encourage everybody to actually try to do these, without going and referring to a unit circle. That just kind of strengthens your ability to use reference angles and quadrants of termination to determine values and signs. But when we look at these here, we could just go look at our unit circle. We need our sine at 45 and our cosine at 30. Our sine at 45 here, look at this, is root 2 over 2, and our cosine at 30 is root 3 over 2. So we're going to fill these in with root 2 over 2 and root 3 over 2, and then go evaluate for the cosine at 45, which I happen to know is also root 2 over 2, same as sine of 45. And our sine of 30 here, this is kind of cool, but whichever one you didn't use here, you're going to use the other part of it, because at the same angle 30, we used root 3 over 2 previously to get the cosine value. We want the sine, it's just the other part of this ordered pair. So it's kind of nice to know that if this is root 3 over 2, this is going to be the 1/2 part of that ordered pair. So evaluating for this, what do we get? Well, multiplying straight across, in each instance we're always doing this, we get root 6 over 4, okay? And this is minus root 2 over 4. And we're going to go ahead and combine this over a common denominator of 4. We get root 6 minus root 2 over 4. And I actually want to put a box around this, and we'll put in real big letters here. This is the exact value. So previously I had begged the question, why would I ever use sum and difference formulas to evaluate for, say, the cosine of 90? I wouldn't, but for the sine of, say, 15 degrees, I certainly would, because here's what we've got. We're able to find exact values for trig ratios at angles that don't commonly occur around this unit circle, at things for which we have exact values, okay? So one thing I want to just kind of demonstrate here is this. If you got a calculator next to you, let's do this. Let's make sure we're in degrees mode. Looks like I'm in degrees. We're going to take the sine of 15 degrees here, and I just want you to see something. We get this big long decimal, but the benefit to using sum and difference formulas here is without using a calculator, we can evaluate for the sine of 15 degrees. We get root 6 minus root 2 over 4. So I'll put this in as root 6 n parenthesis minus root 2, and this is n parenthesis, all divided by 4. What I want you to see is this is an effective way to get exact values for trig ratios that occur at angles that are not common on your unit circle. So let's try this again, okay? Except for this time I want to take a little bit different tack on it. Let's do a tangent. So instead of our sine of 75 degrees here, let's take a look at a tangent of 75 degrees. One thing I notice is that our angle is in degrees, so that's really helpful. We don't have to convert it to degrees. But what we want to do is we want to find some sort of angles that fall commonly around the outside of the unit circle that either add up or subtract apart to be 75 degrees here. And so in this case, I noticed that 45 and 30 are pretty common angles here. What we could do is we could just add those together and say that that's the same thing as 75 degrees here. So what I want to do is we're going to take our tangent of 75 and we're going to rewrite this as 30 degrees plus 45 degrees, because if we can rewrite this in terms of 30s and 45s, we can evaluate more easily here. So using our tangent sum and difference, something that this is the first time we've done this, we're going to take this and expand it here. So we have a sum. And the first thing we do is we always take the tangent of the sum of the angles, or the sum of the tangents of the angles here. So on top, our sine would also be plus, since this is plus minus on both ends here. So the same as what we have on the left, and we're just going to populate this with a 30 and a 45. Now as far as the bottom goes, this is always either 1 minus plus, so if the top is this positive here, this is going to be a minus, and then we just take the tangent of both of these angles and multiply them. So the product of these two tangents. So it's kind of cool. This one's nice because we just use the same two ratios on top and on bottom. We don't have to find 4 separate ratio values. So taking a look at this, what do we end up with here? Well, anywhere we have a ratio we're going to evaluate, I'll just go ahead and put in blank parentheses, but I see that we get this on top, tangent of 30, which if you're savvy here is root 3 over 3, and our tangent of a 45 is just a 1. As far as on the bottom, this is again really cool because I'm going to copy and paste. We're still taking the tangent of 30 and 45, so these same two ratios. And as we simplify this, we get this really, really conspicuous value here. Root 3 over 3 plus 1 and 1 minus, and we multiply these here, we'd get root 3 over 3. And what I want you to do is box this, and I don't expect you to rationalize or multiply by conjugates or anything, but I want you to realize that this would represent the exact value of the tangent of 75 degrees here. Okay, so As you're working with your sum and difference formulas, I'm going to ask you to evaluate trig functions at uncommon angles, but what we're trying to do is really just kind of ask ourselves, what are two angles that commonly fall around the outside of the unit circle that I could either add up or subtract apart to give us this value of this angle that is not common? Cheers.